Okay, so when we last left off yesterday, we got to Turing machines. We saw how the theory of computation led to this idea of what is computable. And from there, we got these definitions of something that is computable is something that can be computed using a Turing machine. And Turing machines are it's a theoretical construct where you have a long string of infinite tape, input output, and a mechanical processor. And this mechanical processor runs algorithms to solve the problems that were given. And these anything that can be calculated can be done with these Turing machines. And they can be very simple. They can be very simple, and it may take a really long time if you're using something like the Charles Babbage's and Ada Lovelace's difference for analytical engines, but eventually they can be calculated, no matter what. There's a few exceptions to that rule, which are things like the halting problem, which is important to know for the things that cannot be calculated. One thing that you may have heard before is something called if something is Turing complete. So this is a way that people refer to programming languages. Is this language Turing complete? What that means is this programming language, can you calculate any of these calculable things? So that's, in order to be Turing complete, something needs to have for loops, needs to have loops, it needs to be able to store variables, it needs to have conditional branching, all of these things that we've talked about in relation to these Turing machines. There's most coding languages that you will use are Turing complete. Let me see. Is there something here? Turing complete. There we go. Turing completeness. So things like JavaScript are Turing complete. C is Turing complete. C#, C++, Swift, all of these languages are Turing complete. Maybe more interestingly, what is not Turing complete? Can any of you think of a language or some coding language that you've used that is not Turing complete? HTML, great example. HTML is not Turing complete. CSS, also not Turing complete. These, I suppose you can think of maybe HTML as Turing complete if you include like script tags and embedded JavaScript, but not really. HTML plus CSS is apparently. I'm curious how that works. There's some interesting. If there's a lot of some people have gone to great lengths to make Turing complete things that you would not expect to be Turing complete. For example, let me see if I can find this cellular automaton. Cellular automaton is a very, very simple algorithm that is used to update cells, and it looks something like this. But apparently, this is Turing complete as well. I'm not sure I quite understand how this thing is Turing complete, but apparently it is, and apparently it's been proven. And this is something that you will be experiencing for yourself in a few weeks for Project Week. This is a really fun project. So maybe you can figure out how this is Turing complete for yourself when you implement it. But basically, I think what they're trying to get at is you can do loops, you can program values using white and black as to simulate binary, for example, and you can solve problems using this. In Minecraft, you can see people who've built processors in Minecraft using Redstone, for any of you who are into Minecraft. So there's a lot of ways to do Turing completeness. And the interesting thing about Turing completeness is that anything that is calculable, everything that is computable, can be solved by by a Turing complete language. So all of these programs that you're writing now, these arrays, these pretty much anything, all of these complicated algorithms like counting stairs and things that you did before, that can be solved using cellular automaton or any other Turing complete language. So that's someone in a previous cohort sent a link that I thought was really interesting, like surprising Turing complete. Is that what it's called? Accidentally Turing complete. Maybe it was this one. But anyway, there's some fun things you can see that Turing completeness in weird places. There's some fun stuff you can see of Turing completeness in interesting places. All right, I don't know if that's what it is. C# is definitely Turing complete. C# is Turing complete. So I don't know if you put that as something that's not Turing complete, but C# is definitely Turing complete. All right, so that's Turing machines. Turing machines, again, as an overview: input, output, and a long string of infinite tape. Now we've seen how that's evolved, how the long string of infinite tape has come to be used as memory, and we have this long array that we think of, which is indexed by memory addresses in modern computers. So we're going to take that a step further today, and we're going to see how that got to what's called the von Neumann architecture. Now, for a long time, I thought this was von Neumann, and I think it's just because I read it all the time and I never heard it out loud. But I recently learned from Sean that it's pronounced von Neumann. So remember that this is von Neumann model. But if you look here, it looks very similar, right? We have inputs, we have some processing, and then we have outputs. Within the processor, we have these two things called control unit and the arithmetic logic unit, which we'll be getting more into tomorrow. And then we have our memory. So this is very similar to a Turing machine. You have the input, output, some processor, and then memory. And the memory is like a long string of infinite tape. So this is the same model that all of our computers use today. If any of you have built a computer from scratch, it's actually not as difficult as you think. You can order parts online, and you can buy your chip, you can buy your main processor, you can buy a motherboard, you can buy your little memory slots, and input and output. Of course, you've probably bought a keyboard and mouse for inputs. You've probably bought a monitor and speakers for outputs. So this is very similar to what a computer looks like today. And it's actually really fun. You can buy a case. When you buy your motherboard, there's these little slots, so you can really just plug in all of your different computer components and build your computer from scratch. And everything works just fine. It's pretty cool. Now, this model is it is like Legos. I think this is something that people like me who grew up playing with Legos, it's really fun to put that stuff together. However, there's it's also, I don't know if it can be good if you're really trying to get a lot of performance out of your computer, and if you want custom things, like if you don't really care that much about processing, but you want a really good graphics card or something like that, you can customize your components. But there's also some possibilities for making mistakes. Like my first time building a computer myself, I put way too much thermal paste on my CPU chip, and it got all over the place, and I kind of wrecked a very expensive piece of hardware. So for those of you who like that stuff, it's kind of fun to build, but it's also a little bit of a pain. Like after that first time, I just buy my computers now, and it works pretty okay. Also, I just buy Macs now, which are all put together for you. I've never had a CPU explode, but I've seen some horror stories online. I've also seen horror stories of like old computer cases with spider webs and massive dust bunnies, which is even more horrific to me. Like animals and like egg sacs and things like that. Can be pretty disgusting. So clean out your computers. RAM catching on fire. These are fascinating stories. I think so. There's if you have like power sources, or if you overclock your computer, there's definitely things that you can that can go wrong. We're going to talk. Let me see. Are we going to get to clock speed today? We're going to talk about clock speed and overclocking and things like that. Maybe tomorrow, or maybe today if we get to it. But okay, so let's see. Von Neumann architecture: control unit, arithmetic logic unit, input output. So this is a theoretical model. And if based on this theoretical model, there's some problems. Like for example, if you look in the Wikipedia page, there is a bottleneck which occurs because data operations cannot occur at the same time as instruction fetches because you only have a single input and output bus. Now, a lot of these things have been addressed using modern architectural niceties. Things like caches, things like let's see, what else? Things like external storage, and also with the CPU, there's specialized chips, like you have a graphics card. So graphics card are outside of the control unit and arithmetic logic unit, but it's used only for operations that are used frequently in graphics. Things like drawing triangles, rendering, and stuff like that. You also have sound cards, which do the same for audio, for processing audio. So that way you don't have to bog down your main software by with things like expensive graphics calculations. So this is where things like graphics cards come in. Caches. So cache, you may have heard the word cache before in computing. Now caches it's basically a little temporary storage space that's really fast. And they occur all over different layers of computing. For those of you who are web developers, you may have heard people saying like, "Oh, you need to clear your cache," or "This is stored in cache storage." If you've written JavaScript, maybe you push some code and it didn't get updated because the JavaScript is in the cache. So modern web browsers, every time you download an image, every time you download things like JavaScript or CSS, they'll get stored locally in a cache. So then next time when you load the page, you don't have to re-download it again. And it gives you a little bit of performance boost. This can also lead to you holding outdated code. So you need to do things like cache busting, which is you change a timestamp, which lets them know that you need to re-download it again. Caches also occur on servers. So sometimes when you have like a dynamic web page, if you have a static page, caching doesn't really get you anything. But if you have a dynamic thing, like the front page of a news site, for example, like New York Times, for example, let's see, if we go to the front page of NewYorkTimes.com, you'll see that there's all these articles, right? And these are all loaded dynamically. So they probably have some CMS. CMS stands for Content Management System. Some CMS that says, all right, this is pointing to this article, this is pointing to this article, this is pointing to this article, and their editors will update this probably at the beginning of the day. Now, this is all dynamic. So they're doing database queries here. So this article will have like an ID in the database, and they'll be loading like, all right, article.headline and article.tagline and things like that. So every time you're doing that, you need to look at the database. As you imagine, that's a little bit of a slow operation. It's slower than just loading static pages. So all of this stuff, once it gets loaded, it gets stored in a cache. So now it's just storing all of this HTML that's on the front page. That's all stored in a cache. So now every time someone visits the front page, they just send the cached HTML over to the user instead of having to make a database query every single time. Caches are also in hardware, as we talked about here. So caches include like where do we go? Cache architecture. It means that when you're doing operations, you can cache your operations so that you don't need to fetch them every single time from the CPU or the ALU. Now, one other thing that I touched on that may sound familiar is that this von Neumann architecture, it's not just inside your computer. This is something that's been abstracted to many different places, including to servers. So the internet, this is also basically the structure of an internet. So you have, if you think of this big block in the middle like a server, this is your server code. Instead of a CPU, you have server code. This memory, instead of this memory, you can think of this like a database. And the input and the output you can think of as the internet. So let's think about what happens with the internet. You send like an HTTP request or something, or maybe a REST API request, any request. It goes to the server. The server runs some server code. Maybe it needs to look at the database to pull some data, and then it sends you a response. So this architecture is also used in servers. Things like caches. Caches, as I mentioned before, caches are also used in servers very often. If you look up memcached, memcached with a D at the end, memcached is for distributed memory object caching system. So this is something that's used both on small scale and for very, 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 very large operations. Things like Twitter, things like Instagram, they all use memcached. What this does is it's like let's think about Twitter. Every time someone makes a tweet, then it writes it to the database, right? It writes this tweet to the database. Now, Twitter has so much activity. It has millions of people. I don't know about millions, maybe hundreds, but definitely hundreds of thousands of people at any given time sending requests, saying, what are my latest tweets, right? And Twitter is not just in a single server. Twitter is distributed across many, many, many servers all around the world. So in order to, it's hard for, as soon as someone tweets something, it's hard for that to propagate to every single user. But what it does is it writes it to this memcache, and that's things like Twitter. They have huge memcaches, but this is basically a hash table. Now we're gonna be getting into hash tables very soon, like tomorrow. But basically, you have a key and a value, and the value will be like this tweet, and then you'll say, oh, all right, tell me all of the latest tweets, and one of the keywords here is distributed. So this cache gets once you push your tweet, it gets distributed to all these different caches, all these different memcached caches, all to these distributed servers, and then when you say, all right, give me all the new tweets, then it will first read the memcached, and it'll send you all the new tweets from there. This works really well for Twitter because Twitter is all about like the instant tweets. Memcache does not work for old stuff because once the cache gets full, it drops out the oldest stuff. CPU caches work very similar. So CPU caches they store like the most recent things, and once the old stuff. So there's something called an LRU cache. LRU stands for least recently used. LRU cache. I think there's a code challenge on this. I don't know if you've had this the LRU cache yet, but if you're interested, you can look at this. This is an application of a doubly linked list. They're implemented using LRU caches are implemented using doubly linked lists. You can also think of it like a queue, where okay. So what is the queue again? What is the order that things go through queues? FIFO, first in, first out. Yes, that's exactly right. So first in, first out. So a queue is like a line, right? Like the people who get there first, they get served first. The people like the things that get in last, they get in last. So this is also how LRU caches are treated. Doubly linked lists are a nice way of handling that. Wait, do I have that right? Am I getting this confused? First in, first out. Yeah. Okay. Yeah, that's right. Because the first thing in is going to be the oldest thing, right? I always have to think about this to make sure. So the first thing in is going to be the oldest thing, so it's also the first thing out. And if you have something that was used more recently, that gets put in the back of the queue. So anytime you want to add something new to the list, you just pop out the oldest one. And the other half of that is going to be a hash table, or you can see here hash map. Hash maps are pretty much the same thing as hash tables. I'm talking about all this hash table stuff sort of as a preview. We're going to be diving into exactly what that is tomorrow. But just remember that hash tables go by many different names, including dictionaries in Python, objects in JavaScript. I'm not sure what they are called in Swift, but probably the same thing. Yeah. So Brian, CPU caches. You're right that they're usually pretty small, and CPU caches are faster than memory, than RAM, but as you mentioned, they're a lot smaller. There's also one level even faster than that, which is registers, and registers are only like a few bits. So registers are like a temporary storage space for when your processor is doing arithmetic calculations. It's basically like some storage space. Like when you're adding two numbers together, like you have your first number, your second number, it'll get put in the register, and then while it's doing the operation, and then it'll spit it out. So yesterday, I also alluded a little bit to the idea of virtual memory, and that's the cache is part of that. So you go to the register first. The register is the fastest and also the smallest, and then you get to the cache layer, which is a little bit bigger and a little bit slower, and then you get to the RAM/memory layer, which is a little bit bigger, or actually a lot bigger, and but a little bit slower than the cache. And then finally, you get to your hard drive, which is humongous compared to your cache and your memory, but much slower. So your program doesn't really have a sense of all of this. This is all handled by your operating system, or your kernel, to be more precise. So we don't have to worry about those things. All we need to do as a programmer is worry about things like malloc. And when you get to higher level languages, you don't even need to worry about that. So be happy that you're a programmer in this day and age, where we have nice things like high level languages, and we don't have to deal with all these details. All right, let's see. I think that's all I wanted to say about von Neumann architectures. This is something that I want you to remember, and that hint might be coming up in your interviews at the end of the week. But when you think about what is a computer, this is something that you want to remember. A computer at its very core is these components. So you have inputs, you have outputs, and then you have a processor and memory. So inputs, outputs, processor, and memory. You also want to remember that the processor is broken up into a control unit and an ALU, arithmetic logic unit. We'll be jumping more into that tomorrow. Maybe if we have time, we can do this. But I also want to get to C and start going through your C questions. So maybe we'll just save this for tomorrow. Or you know what? No, let's just jump into it today, since we have time, because we have hash tables to go through tomorrow, and that's a pretty meaty topic. So central processing unit. We have control and we have arithmetic. Now, when we've been working in C, which I've been calling a low-level language, right? And compared to the languages you've been working with earlier, C is pretty low level. It means you have to worry about things like memory allocation, freeing your memory, dealing with actual pointers and stuff like that, which at a high level, like Python, you don't even need to see at all. Back in the day, and by back in the day, I mean not even that long ago, like maybe 15 years ago, 20 years ago, C was known as a high-level language. And the reason that is because C abstracted away a lot of the stuff that I just mentioned to you now, like dealing with register memory, dealing with machine code. Now, I don't know if Tom is here, Tom Tarpe, but I know that Tom has done some assembly, and assembly is what's known as machine code. So if we look up assembly, we can get we can see what this looks like. So when you write C and you hit compile, or if you type make, what that does is it turns your C code, which is nice and fairly human readable, and it turns it into something like this. This is assembly language. Now, this is something that your computer can read. You have an instruction, you have a value 1 and a value 2. Now, computers can only do operations on 2 numbers at once, or 2 values at once. If you do something like 1 plus 2 plus 3, what it'll do is it'll take 1 plus 2, it'll take that result, and then it'll add 3 to that. And that's an architectural limitation. So here on first you have an operation, and then you have the value 1 and the value 2. And each of these values can only be a certain number of bytes. Now, depending on your architecture, that could be 32 bits or 4 bytes, or it could be 64 bits or 8 bytes. But you are restricted to a certain width. Now, when you write assembly code, usually you'll have something like add instead of C003, but that again gets converted into something that the computer can read. And different chipsets will have different assembly codes. So things like Intel will have their own specific machine code that their computers can run. Same with like Motorola will have their own. This is down to the chip level. Now, this is also why different computers will have different compilers, because they need to convert your C code, and C should run on pretty much any computer, and it'll convert that C code into machine language that your specific chipset can read. Now, let's see. So when you think about it that way, things like C are high-level languages compared to this. You don't need to worry about what your chip can read, what your computer can read. All you need to do is write things like for loops and variable assignments. Things like memory allocation, those are handled with nice things like malloc. Now, I know for you, malloc seems really obtuse and really tough to deal with, but imagine coming from something like this, writing code like this, and then going from this to C, and you'll start to see how amazing, how C used to be known as a high-level language. All right, so there's 2 types of these instructions. One is going back to our von Neumann architecture. One is things like control units, and then one is the arithmetic and logic. So these are mostly handled by the ALU. These are things like add, subtract, multiply, like the arithmetic things. There's also goto commands, and these are handled by the ALU. And these numbers are instructions, and the instructions are stored in separate parts of the chip. So that's sort of how these 2 things are divided up. We're gonna get lower level starting tomorrow, and get actually all the way down to the transistor level and see how these things work. But that's just a short preview. Yeah, I think we'll save some of that for tomorrow, and we'll jump into C soon. Well, I got through that pretty fast. Are there any questions about any of this stuff? I know this is just this is sort of a big dump, but any questions so far about any of this stuff? It looks like no. Anytime you do computing, you think about it in terms of this. Try thinking about it in terms of this. The iOS people, of course, this is your input and output are your screen and your audio, and then you have your chips and you have your memory. This is down to the theoretical level. This is how a computer works. And you can, if you look at this model, you can think you can probably create a computer, very simple computers using a number of different components. If you look at things like Raspberry Pi or embedded systems or microchips, there you can have things like this. Sometimes maybe you don't have input or output. Maybe you just have like an embedded chip that just runs things on its own. I mean, usually you'll still have an input or some sort of input or output. Maybe it doesn't need memory. Maybe you don't need to store any stuff, and it just takes stuff, runs some processing, and spits it right out without needing to do any memory. But even still, it probably has some cache, or it has some little thing to do to store values while it's running calculations. So at its core, you'll see this basic architecture in every single computer. All right. If there's no questions about this, I will. Why don't we, before break, I'll start jumping into. Or do you want to take a break now, and then jump into C, or do you want to just move on for right now and take a break in 10 minutes? Okay, we have one, keep moving. Any other, okay, let's just keep going then. All right, so let's see. I saw a lot of these questions seem to be on similar things, which is good because it lets me know that these are things that that I definitely should go over. So I saw a lot of questions about how to free up memory when you're overriding values. A lot of questions about double pointers. Let's see. One map chunk. I'm not sure about that. I've never seen that before. Okay, so, and then I also saw some questions about testing. So why don't we go through that, because I think that's pretty useful for everybody. So I'm going to start with how I go about developing. So there was a question that came up in Slack yesterday, or I guess not a question, but some students were having trouble developing because all of the tests, as you can see, like these tests won't really run until you've built everything, right? And it's hard to write all of your code and then just hit run at the end and get a million errors and you don't know what's wrong. And that's just a tough way to develop. So students were wondering if there was a better way to go about developing in C specifically. And what I recommended is to start using to make use of this main function. This is an example I want to use later, so I'm going to comment it out. So what I provided for you in the test file, what you were given is this basic main function. Now what this did, if you look at it, is it creates an array, it inserts a value, it appends a value, it inserts a couple more, it prints the value, and you remove a value and print. So this is basically a test. This is not comprehensive. I saved that for the actual tests, but this is meant to be modified. All right, you can and should be changing this main function while you're developing. So right now, what do I have? Right now, I created my array, and that's it. Right. So let's say this is let's say I'm working on this as a homework assignment, right? So I created my array, and now I want to see if it works. So let's save. I type make. What is that coming from? Oh, here. So I type make. I'm getting a ton of errors or a ton of warnings. I have one error here, and that's it. So let's see. My error is because I didn't put an S here. So make, okay, 12 warnings and 0 errors. So that's nice. So my errors are coming because none of this stuff is implemented. So why don't I comment this out for now? Make and 4 warning. Okay, so since I haven't implemented these, I need to comment this out also. Make array equals create array. Okay, this is fine because it's unused. All right, so now I'm testing array create array, right? So everything passes and it seems to work. So now let me see if I can work with this. I want to make sure my capacity is set and my count is set. So I can do something like printf %d. D is to print an integer, %d, and then we can do array capacity, array count. Make no warnings, and then we can run our code. Arrays, okay, yeah, you can't really see it here, but it printed out nicely. I'll make some new lines here. New, make, and run the code. All right, so we have 1, we have 0. That seems to be right. We have capacity of 1, we have 0 elements in there. Let's try a different capacity. Make arrays 10, 0. So that looks nice. That looks good. And then we have elements. Now, right now, elements is just an empty array that has been mallocked, and nothing else has come after it, right? So we don't really have a good way to test that yet. We can try implementing destroy. So remember, for every time you call malloc, you need to call free. So here we have a malloc array. We want to do it in reverse order. So we mallocked our elements. So we can do free array elements, free array. We don't need to free our capacity, and we don't need to free our count, because these are captured when in this malloc. So when you malloc space for the array, that's creating this space. The reason we need to free elements is because this was mallocked separately, right? And I'll drop this stuff into Python tutor so we can see what this memory looks like once we get to a point where it makes a little bit of sense. So let's and also this isn't complete yet, but this should work for now. So let's free our run destroy array. I'm actually curious what happens if we print this here. I think it make arrays. Okay, so interestingly, even though we freed it, it still shows our stuff, which I'm not totally sure why that is, but I guess it's compiler specific. We can drop this into Python tutor here. I know it's a little weird that it's called Python tutor, but it's running the C code. But so let me copy this. We'll drop in our main function. And end. Wait for it to compile and step through. All right, so we're creating our array. We have our capacity. Capacity is 10. Looks good. We're declaring we malloc our array structure, and we have space for capacity, count, and elements. Looks good. Capacity set, count is set, and now elements. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 empty slots. Now, since we use malloc, we have these question marks here. What these question marks mean is that we don't know what's in there. We have no idea what is in these slots. It's what's known as garbage. So I think that was one of the questions up here. What's the difference between malloc and calloc? The answer is that when you use calloc, it sets all of these things to 0, which can be nice. It's good if you need your default values to be null, but if you don't care about your default values, which I don't think we do for our arrays, then it's a little bit faster to run malloc, since you don't have to run the operation of setting everything to 0. All right, so we did this. Our created array looks good. Now let's destroy it. So first thing we did is we're freeing our array slash elements. As you can see, it sets that to garbage, which is nice. And then we freed our array, and we're at the end, and there's nothing left. Okay, so this one throws an error. So this throws an error because we're trying to read this array which we freed. So I don't know, I'm not sure why it runs, why it allows us to look at this stuff on my computer, but it throws an error here. But in general, after you free something, you should not be accessing it because you have no idea what's there. Freeing something means that you no longer have a reference to it. So your computer is free to assign that memory to someone else. So they can put something else there, and if you're reading it, then you have no idea what's going there. So I don't know why my computer is still letting me read from it, even though I freed it. But Python Tutor doesn't like that. So that's good. All right, let's keep moving. So resize, let's skip that for now. Read, let's do append. Resize the array if the number of elements is over a capacity, or throw an error if resize isn't implemented yet. So we have not implemented resize yet, so let's start by just throwing an error. Do you need to loop through each element since they are pointers to pointers? Yes, Brian, we do. So that's getting a little bit ahead. What I want you to remember is to call free every time you call malloc. So every time you call malloc, you need to call free. So that's what I want you to remember. And here we called malloc twice, so we need to call free twice. And now as you'll see, once we start inserting and appending, we will be calling malloc again, or it's actually going to be a hidden malloc inside of string dupe, but there's still, even though it's a hidden malloc, you still need to call free for that. So we will get there. All right, so to insert, we will do, we'll check our capacities first. So if we're appending, we need to do if, let's see, if array capacity is less than or equal array count. Is that right? So if the capacity is less than or equal to the count. How come you don't have to free every single character? I'll talk about that once we go back to add that, but I haven't forgotten. So if if the capacity is less than the count or equal to the count, that means we're at capacity or over capacity. Now it should never be over capacity, but we'll just do this here because it's a little bit safer. So if the capacity is less than the current count, then we need to throw an error. So we can do printf standard error, and then let's make our error something like index error, index E is out of range. This is what the Python error will throw, and we can do index is out of range. We don't need anything after that. Otherwise, we know we need to return. You can either return here or do an else. Are those out of bound errors as well? Out of bounds errors. So this should keep you from going out of bounds. This should make sure that you don't go out of your allocated memory. So otherwise, when you use exit, I don't know when you use exit. I don't think I've used exit in C. Exits in C. Is exit just like return? It terminates the calling process immediately. Is it the same as return? Okay, I don't know. Maybe exit does the same as return. I'm not sure about that though. I've never used exit like that. But otherwise, we will let's see. Oh, where was it? Copy the element and add it to the end of the array. Okay, so first we copy char star new element equals string dupe elements. String dupe is the same as malloc and then string copy. So this does is it allocates a new block of memory that's the same size as this string, and then it copies all of the bytes from one to the other. So even though this does not say malloc, there is an underneath the hood malloc. So to answer your question, how come we don't have to free? How come we don't need to free the elements? Well, we do need to free them because now we're calling malloc. So we need to call it a free for each of these mallocs. What if you did it without that call? I'll show an example to show what happens if you don't copy the element afterwards. But the answer is that the short answer is that if you don't do this, and if you just do new elements equals elements, then you're not creating a new string. You're just pointing to the original to this original string. So if this gets modified or deleted or anything happens to that, then all of a sudden your array is going to be invalid. That's not terrible. That's not terrible in this case because maybe that's what you want. But just for safety purposes, I want you to copy it. Why can't you do char copy string lang element +1, then you use string copy? I think that will work. I think that will work because when you do this line, Andrew, I think that's also doing a malloc, right? Because you're declaring an empty block, which is the length of this element +1, and then using string copy. So I think, Andrew, I think that's equivalent to doing string dupe. But string dupe is, I think, a little bit cleaner than this. Okay, maybe you can't. I'm not sure. I'm not. I would have to test. I forget. These are little details that I always forget about C, but like the specific syntaxes. But basically, you do want a malloc to allocate a new block of memory somehow. The test would fail because it would return nothing. So I was curious as to why. Maybe this is not. Maybe this isn't allocating the memory. Maybe it's. I think you would need to do something like char copy like this equals something malloc. I'm not sure. I would have to check and run some tests myself before I answer that with confidence. Is it problematic to have an array of? All right, I'm just going to keep moving with this, and then we'll take a look in Python Tutor. And I think a lot of these questions that you're asking will become clear once we can look at it in this diagram. So all right, where were we? String element equals string dupe. I'll run through this. So array elements of array count equals new elements array count plus. All right, is that it? Let's see. Make and let's try to print out our array. Let's add something there. And then let's try to print our array. See if this works. Make arrays string 4. Yep, so it looks like we were able to append this. Let's do a couple. 1, 2, 3. make arrays string 1, string 2, string 3. Looks good. And let's see what happens if it's too small. We only have 2. Make arrays. Index is out of range. String 1, string 2. Yep. Okay. So cool. So it looks like this is working. Yeah. Marshall, we'll get to that once we drop this into Python Tutor. Maybe after the break. So before we take a break, the last what do we do? We did this simple. We did append, and then we ran this test. Now, as you can see, the big takeaway that I want from this is that we're modifying main to work with our tests as we develop, right? So at first we just had create array, so we did that, and then we tried printing out our capacity and our counts, and it all seemed to look good. And then once we did insert, append, excuse me. Once we implemented append, then we tried appending, and we made this in our main. So to test, we do make /arrays, and we can see if we're getting what's expected. All right. Okay. Let's take a break, and when we come back, I'll answer all of your questions about elements, about double stars, and all the rest of that C goodness. So I'll see you in 5. All right, we're back. Make your way back, folks, and let's take a look at this code that we just wrote. Using GCC, you have to get rid of dash standard equals C99 in order to make string dupe work. Every computer will be slightly different. I think I had to include, is it in standard lib or in string? I think it's in string.h. I had to include this in order to use string dupe. But if that doesn't work, you can also use malloc and string copy. Implicit declaration of function string dupe. Did you mean string comp? String dupe is not the same as string comp. So I don't know about that error. Are you on Windows, Carlos, or are you on Mac? I'm just using the default Mac C compiler, so I'm not sure about any of that. I do have this here, so I think this is defined in the make file. Okay, well that's good. I'm not sure what this even does in the make file, so if it works, fine with. I think that's fine. All right, so let's try stepping through this code, and let's see if we can clear up some of this confusion about double pointers, about what we're doing when we're clearing out elements and things like that. All right, so first we create our array. Capacity 10 array, set our count equals 0. We declare we have our 10 empty slots here. Looks fine. We return our array. Now we're appending a string. This is new. So we take our array. We have string 1 here. We're well within our capacity, so we don't need to print this error. We duplicate our string. So now here's a key. So we took our string and we duplicated it. Now, as you can see, there's these 7 new blocks, 7 new bytes of memory that have been allocated. And now we point to the new element, right? This is a key. So our first element is pointing to the new one, and we increment our count by 1. Now we do the same with string 2. We duplicate our string. We point to the new one. String 3, we duplicate our string. We point to the new one. And now we're done. Now when we destroy, I don't like that. So when you free these, when you free elements, what you're doing is you're just freeing this. So these are actually still here. I don't know why these just disappeared from there, but this would be a memory leak if you didn't free it. So maybe that's not a good example. But what we would need to do for here is loop through each thing. So for as someone mentioned, to free, we would need to do we need to do this here, not in creates, in destroy. For int I equals 0, I is less than array, count I plus plus, free array elements I. So we need to go through each of those strings and free them individually. And then we can free our elements, and then we can free our array. All right, so why do we do this? Why do we do this? It's because we allocated memory with string dupe. Yeah, I caught that, Anthony. So we allocated our memory with string dupe here. So again, under the hood, string dupe is a malloc and a string copy. So since there's a malloc underneath, a hidden malloc, we need to also do a free here. and then we free our elements, and then we free our array. Let's back up and see what's going on with all of this stuff. So these we have these three things. We have our array struct, we have our elements array, and I know it's a little confusing that this is capital A array and this is lowercase a array, but remember this capital A is the struct we defined. Maybe it would have been better if we called it something else like my array, but just I guess just bear with me. So we allocated memory for our struct, we allocated memory for our array, and then we allocated these three strings. So we need to when we free our memory, first we need to free this, and this. If we freed this one first, if we freed this first, then we would lose our references to these strings, so we wouldn't be able to free them. So we need to free these strings first, and then we can free this, and then finally we can free our last thing. So let's go back and add this in. Put this here, run our code, and see what happens. Let's get ahead a little bit, adding our strings. Now let's get to back up. All right, so now we free our first element, our second element, our third element, free our elements, and then we free the final array. And then we're done. Should we free the allocated memory without an assigned value also? Let's back up. So are you talking about like 3, 4, 5, 6, 7, 8, 9? So these aren't pointing to anything. So these are not pointing to any slots. So there's nothing to free here. This memory you do need to free, but that's handled when you call this line, free array elements. So yeah, these are not pointing to anything. Now, okay, so a lot of people are confused by this. Why do we have a double pointer, right? Okay. Now this is a tricky thing, and I think you may get a little more confused when we get to hash tables, because in hash tables we're going to be using double pointers, but it's going to be something different than this double pointer. All right. So bear with me here. The first thing that you want to remember when you look at these things is you can think of a char star as like a string, right? So when you have a pointer to a char star, you want to think of that as a pointer to, so this is an array of strings, right? This is an array containing strings. Now you wouldn't, look at our array. Remember, our arrays are defined as a block of contiguous memory. How would you store this? How would you store this if instead of a char star, you just had a single pointer? What would this do? Well, that would mean that each of these blocks, instead of pointing to another thing, your string would have to be contained in each of these blocks, right? So this block would have to be string 0, this block would have to be string 1, and this block would have to be string, sorry, this block would be string 1, this block would be string 2, and this block would be string 3. Well, there's not enough room to put a string here, right? You only have one block of space here. Now, I guess you can make it a really big block. Like you can make this block 7 and this block 7 and 8. These are actually 8 bytes. So you can make this 8, and this 8. But then what if you want to do a string that's longer than 8 characters, right? You wouldn't be able to fit it all in here. Yeah, Marshall, that shouldn't work, right? Like, I guess so. So this is a char star. So this right here, this is a char star. So you can think of this. What if elements was pointing to something like this, right? Each of these slots can only hold one character. So you would not be able to have a string in here. You would only be able to put one character. Now, if you just wanted an array full of characters, that's fine. That's what these strings are. It's just an array full of characters. But since we want to store strings, you need to be able to have variable length. And since, as we discussed before, arrays cannot have variable length, their size needs to be determined up front, then you need to have a pointer to you need to have a pointer to a pointer to a character. And a pointer to a character is how we think about strings. Does that make sense? So think of so this is not real. There's no string data type, but you can think of it like this. So this is a string. So this is a pointer to a string, right? And a string is equivalent to a car star. So this is a pointer to a car star is just a car star star. You could of course make this like a triple and have a pointer to a pointer to a pointer, but I guess that's if you wanted to have a pointer to a list of strings. Does that make sense? Yes, Andrew. If you wanted to do that, you would need to change this type. Now, if we look at CPython source, I dropped this into Slack, but I think it's kind of interesting. I hadn't looked at this before, but you can actually look at how Python implements their lists. Where is it? List object. So even though there's a ton of crazy C code, you'll notice a lot of it looks quite similar, right? So here we have our objects. We have a pointer to our double pointers for items. We have allocated and bytes, and I think there's a size here somewhere, new size. All right. So they're doing basically the same thing. They're pointing to a list of they're pointing to an object pointer. Now the reason I said this might be confusing is because an object pointer is different from a character pointer. So that's like when we're creating our struct, we have an array star instead of just returning an array, and that's what's going on here. So this is an object, a generic object, a pointer to a generic object, and then we have a list of these generic objects. And then we have our size, and we have the allocated bytes. And then if you look at here, this comment describes how Python does its resizing. So as we mentioned, it over allocates proportional to the list size, making room for additional growth. And the over allocation is just enough to give linear time amortized behavior, which is a very complicated way of saying that it gets bigger each time. So you need to resize the array more infrequently as it gets bigger. Brian, regarding the star and the star star, I think you're referring to keyword args and I forgot what it's called. Basically the list args and the keyword args, right? Yeah, there you go. Star args and keyword args. I think that's where it came from. I don't think it's an exact. I'm not sure that it's actually a pointer to a pointer, but I think that this convention is where that came from. But I don't think it's a direct parallel. But this is definitely where it came from. This is definitely a reference to C. Okay, so that's why we have these car star stars. You're going to see this again when we get to hash tables, and instead of a car star, you're going to be implementing another struct for what you're storing. But for now, I hope this makes a little bit more sense. Is everyone feel comfortable with this notation, the car star star elements? If anyone wants me to go over it again, let me know in Slack. Let's see. All right, we have. So this is the home. This is most of the homework. We're missing array read, but I think this is pretty simple. If you haven't filled this out, then I think you should be able to complete this. Is anyone else? Does anyone? Let's see. How many? 40% of the class got stuck on these, on create, destroy, and append. Let me see. Maybe let me ask a poll. Only questions about create, destroy, append, read. Multiple choice. Let's make it yes, no. Advanced options, anonymous, submit. All right, any more questions about create, destroy, append, read? If it's a yes, then add your comments, add the question in a comment below. I think I covered, what else? Okay, so we have some questions about resize. Oh, here's a good one. Do you need to set each array equal to null before or after free? So when you're freeing stuff, you don't need to set it to null. Where you do need to set it to null is if you're when you're removing something from the array. Is that true? Maybe you don't need to set. Maybe you don't need to set it to null. I thought there was something that said their tests were failing when they didn't set it to null. Where is that? Null. Why do you need to set it to null before freeing a pointer? When running, it gives an invalid pointer, but setting to null beforehand fixes it. Okay, I think what this is referring to is, Tom, when you did your free, did you do from I = 0 to count or to capacity? Because I think if you did capacity, which means you're trying to free elements that haven't been allocated yet, then I think this will throw an error because you're trying to free stuff that hasn't been allocated yet. I think if you do free of null, that's a special case where it lets you just free of null does not throw an error. So I don't think you need to do that explicitly, but you need to make sure that you're only freeing elements that have been allocated first. All right, we had another question about what calloc does versus malloc. This is a good question. Let's go back to our C tutor and see if we can. Shoot. Too late. All right. Well, if you remember, malloc. Let's change to calloc. Capacity, size of char. So to reiterate, what calloc does is it will set everything to 0. It'll malloc, and then it'll set everything to 0. So here, when nothing has been set, we have these question marks, right? What question marks mean is that you just have garbage. And what garbage is you don't know what garbage is. When you ask the computer for memory with a malloc, it gives you a block, right? But you're not the first person to use that memory, right? Like your memory is this big tape, and memory gets freed and allocated all the time by different programs, by all different kinds of things. So when you get a block of memory, you don't know who was there before you, right? It's like you go to a restaurant, you're sitting at a table, you don't know who's sitting there before you, right? You just know that now that table is yours. Where this comes in, what this means is that maybe someone owned this block before you, and they wrote a bunch of stuff that you don't that is not 0, right? Maybe they were storing a string here. Maybe Spotify had this memory before, and this is the name of the track you were playing. Who knows? That's why it's a question mark, because you don't know. You don't want to read it. You don't want to be reading that, and C will get mad at you if you try to read it. Although there is ways to look at this. So what you do is, when you get your new thing, is you want to overwrite all of these values. So in our structs, we malloc it, and we have question, question, question. So we want to write these over. Now here we did calloc. So maybe if you remember before, instead of null, these things had question marks before. And that's because when we just call regular malloc, this stuff all gets filled, is initialized with garbage. That means we just get this block and we don't know what's in it. Whatever the last person to use that block of memory put in there, that's what's going to be there. When you call calloc, then it gives you that block of memory, and then it writes it all to null. And again, null is just 0. So it's going to be 0, 0, 0, 0. So just all zeros. It's going to fill everything with zeros, which is going to give you a nice clean slate to work from. That can be important if you're doing things where you need to check. Like if you want to see, has anyone put anything here, you can do a check if like element number 3 is null. We're not doing that here, but if you need to do null checks to see if it's unoccupied, then you'll need to calloc it first. Otherwise, if you try to check if it's null before, you're just going to get an error because it's not null. It's going to be garbage, and garbage is not the same as null. Calloc is better for most things, but why use malloc? It's because malloc is faster. So calloc is doing two things, right? Calloc is allocating and then writing. Malloc is just doing one thing. So malloc is just giving you this stuff. So the time you would use malloc is if like for example, when we declared our struct, we don't need to calloc this, right? We don't care about allocating it because we're going to be writing it over anyway. So there's no point setting this to 0, 0, 0 if we're just going to write it over to 10, 0 pointer immediately after. All right, so malloc is just slightly faster. Calloc is good if you need to fill stuff with nulls, which you will be doing for hash tables. So don't forget about calloc. Okay, for array read, the instruction says to throw an error if the index is greater than the current count. Can you go over that? Because mu assert read array 0 value initialized is not null. Yes. Okay. So where is that? So that's for read. Is that for read? Yes. This is basically saying that when you're doing read, so we need to have a return value, right? This says that we need to return a value, but if we have an error, that is our index is out of range, or then we're gonna need to, we throw an error using something like, where is it? Where's our error? All right, we throw an error like this, and then we need to return something. So in read, we would do this, and then we would return null. So that's what this is saying. That test, I think the wording is a little bit confusing. What this is saying is we're trying to read something we're trying to read in elements, but there's no elements in here. So if you look at this test, what do? We create an array with capacity 3, and then we're trying to read the first element, but there's no elements in our array. So it should throw an error and return null. So that's what this is checking this. Value initialized is not null. So I think what's confusing is that you're confusing that this is the null return value versus like the initialized value. So this null is coming from the error, not from the initialized value. So then once we insert a value, then append should append. Once we insert our value, then we should be able to read. Where's the mu.read? Okay, there's no mu read. Mu assert read. I guess there should be a test here that says read equals. Oh, it is. Oh, yeah, it is. Oh, I'm sorry. I'm confused. So we read this, and now we call the same thing as this, but now we're getting our actual value that we inserted. So yeah, I think it's just the wording of this test, which is not great. But that's all this is saying. It's if you throw an error, you should return null. Otherwise, return an element at the given index. I guess we can just fill this out since it's only one more line anyways. Otherwise, return array elements of index. And I think our test should pass now. Well, we'll comment out our day 2 tests. Make arrays, make sure this all runs. All right, make tests. Error linker commands. All right, inserts. Oh, okay. Well, what's going on here? Inserts, not commands. Okay, because our header values are not defined. That's annoying. Do we have to comment this stuff out? Yeah, C can be a pain. Make tests. Seg faults. Make tests. All right, so our tests pass now. Our day 1 tests pass. So what I did is, since my day 2 stuff isn't filled out, I just commented this out, and my day 1 tests passed. All right. So where were we? So assign null. You will want to assign null to values. Do you have to assign null when you free them? Yeah, I don't think you need to do this. When you destroy array, do you need to set? Is the same thing. The same rules apply in resize elements when you free the old elements. When you are resizing, you need to, once you create your new resized array, then you can just call destroy array on the old one, and it should clean everything up. But you don't, no, actually you don't, because you don't want to free your original elements. Let's look at our C-tutor again. All right, whoops, back, oh no. Okay, so we have this, right? And let's say we call resize array, and we want to copy all of this stuff over. What you're going to do is you're going to create a new elements, and that's going to be twice as large as this. It's going to be size 20, and then you're going to want everything to point to these strings. Now you want to clean up the old stuff. You want to clean up this one, this array, and this struct, because you're going to have a new one. But you don't want to clear this stuff up because your old ones are going to be pointing to this. Now you could just string dupe them, I guess, but that's a little bit redundant since you're going to be pointing to the original ones anyway. So that's what's going on with that. If car star elements points up to a list of pointers, do you need to free up each individual pointer first? Yes, you do need to free them all in when you're doing free. Munmap chunk. I don't know what munmap chunk is. Invalid pointer. I'm not sure what munmap chunk is. I've never seen that before. What does that mean? Invalid pointer, I guess. Maybe it means you're pointing to garbage. I'm not sure. I'm not sure where that came from. But it seems a couple of people got that. As far as what does it mean, I would say just Stack Overflow it or Google it, because I'm not sure what that is either. I see we write car star variable name, but I'm curious if we ever declare car variable name with no star. So again, this is just a single character. So if you don't have a car, if you don't have the star, then you're just pointing to a single character. So that would be that's if you only want one thing. So when you have your car star, you're having a list of characters. Each of those is going to be one character. So that's but when you have, if you want to have a string, then you need to have the star there. When you create a struct array with an array in it, are you supposed to allocate space for all of the pointers? Yes, you need to allocate space for your pointers, but you don't need to allocate space for the strings until you create the strings. But you do need to create the space for the pointers. That's what this is. So you need to allocate this all at once. And then the strings you can allocate one at a time. How much extra code does a language like Python have for handling edge cases? The answer to that is a ton. As you can see, this is a humongous code file. And if you look at the repo, there's way more code. So Python has a ton of code. We're implementing a very, very simple language, but the core is still the same. The basic stuff is very similar. Also, I wanted to point out, remember, there's a question about how Python has lists with multiple different types. That's because they're pointing to this generic Python object, and then like a list will inherit from this generic object. So will a string. So will integer, and everything in Python is a type of Py object. When appending elements to an array, does it consider existing elements when you are doing a check for capacity? I.e., array appends with this 1, 2, 3, 4 elements ready to be inserted. Okay, so remember that this 1, 2, 3 null null null, this is just your over allocation, right? So if you were to print this out in Python, it would look like this: 1, 2, 3. Sure, there's also null 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 afterwards, but that's not actually a part of the array that you're looking at. When you're adding a 4, a 5, a 6, and a 7, then you're just replacing those nulls, 4, 5, 6, and then you run out of space. So when you're adding the 7, then you need to resize your array, and that'll be this with like some nulls here, 1, 2, 3, 4, 5, 6. So you need to copy all of this over, and then you can put your 7 here. Is that the question? Is that what the question was? Okay, cool. Why do you need to set it to null before freeing a pointer? Oh, we talked about that. How to implement variadic? I don't even know what that word means. Variadic functions with optional args in C for things like pop. In Python, we had args equals none. Oh, okay. I forget how to do that in C. I forget how to do it in C. I know how to do it in other languages, but I think you can do something like void array pop equals something, and then do array pop car star or index, and then something else, and then maybe you could define this as, oh, you need to array star array. Maybe you could define this as array pop array, and then array count. I don't know if this actually works though. We could try it. We need to do make array conflicting types for array pop. Okay, I guess that does not work. Okay, the answer is I don't know how to do that in C off the top of my head. I would need to look that up. I don't know if you can. I'm not sure if you can even do that at all. I mean, you could just define it like this: array pop with index, which will work. All right. Huh? Why am I still getting an error? Previous implicit declaration. I think I need to put this up here. Make. All right, that's giving even more. Okay, I think this is fine. Well, language is the .sh file written by. sh is shell, so that's shell commands are like terminal commands. So if you want to do like test.sh, you can do ls echo hello, and you can run sh test.sh, and it will do the same as doing ls echo hello. So sh stands for shell. It's for running shell commands. All right. Can you explain the difference between one pointer and 2 pointers? So again, 2 pointers is just a pointer to like an array of pointers. No, or not even necessarily an array. It's just a pointer to a pointer. So you can think of it like if you think of it like nested things. This is a pointer to whatever is before it, and if what's before it is a pointer, then it's a pointer to a pointer. Which sounds really confusing, but when you look at something like this, I think it makes sense, right? Because you have a pointer to this array, and each of these are pointing to their own strings. And this is like a car star, and this is a car star star. So hopefully that makes sense. I really like these. I really like these visualizers because I think it makes it so much easier to understand. When I learned this, I didn't have Python tutor, and C made my brain hurt quite a bit. So, I think this tool is really cool. This actually helps me understand it even better as well, better than I did a few months ago before I started going through all of this stuff. So when you dereference star star, would it be a star? Yes. So when you dereference a double star, it gives you a single pointer. Or like if it's a character pointer, then it'll give you the string. In array.remove by trial and error, I found that we needed to set the array element to null before freeing it. I think we talked about that before. I think you only if you remove, so I think you can wait. This is in remove. We haven't gotten there in the code yet, but I think like if we were to remove this one, I think you can if you free this string first. So you free this string, and then you don't need to free this. You don't need to free this pointer. So you would free string 1, and then you would scoot everything over. Then you would scoot this to here, 1 to 0, 2 to 1, and then whatever's in 2 would still be pointing here. But as long as you decrement the count, you don't even need to overwrite this. You'll have redundant pointers, but if you ever get to 2, you're gonna move over 1 anyway. Does that make sense? So I think if you're removing something, you need to free this. You need to free this string, but you don't need to free like this slot, for example. When is it better to use malloc versus calloc? We covered that. You use malloc if you're gonna immediately overwrite your values, or if you don't care what's in them. What is the value or best utilization of the double pointer? Double pointers are when you need to point to like a struct. Structs are, even though So even though we the struct is an array, we almost always refer to structs as array pointers, and I think that's something that will make more sense when you start working with hash tables, because then instead of storing strings, we're going to be storing another struct as well. So then you're going to see another application of double pointers. That's also that's a lot more. That's similar to what's going on here with this double pointer. Is it good practice to free an element pointer? All right, so this question has come up many times. So I want to make sure that everyone is clear on this. Is it good practice to free an element pointer to null before running free on it? So you should not have to do that. You want to free this, and then you don't have to free the slot. For example, what that means is, like, if we were going to free something here, we would do. So if we're just freeing one thing, like if we're doing in remove, where's remove? Let's say we're freeing something here. We would just have to do like free array elements index. We don't have the index here. We would have to find it, but we would just have to do this, and this is enough freeing. Like we don't need to do free elements. We don't have to set it to null either. Does that make sense? So we don't need to set anything to null here. All we need to do is free the string. And what that's doing is it's just freeing this block of memory right here. We want to keep this block open. So we want to keep this block allocated, and we don't free that, but we want to free this thing that this block is pointing to. All right. Free elements. What is a vector and how to implement it? So a vectors are similar to these things that we're implementing here. Vectors are in C++, I think, only. Vector, let's look, vector C. Yeah, vectors in C++. Okay, well, if you want to see how to replicate a vector in C, let's see what Stack Overflow says. In the days before C++ and vectors and lists, how do you expand the size of an array? So this looks a lot like what we're building here, right? We have our capacity, we have our size. They're using size t, which is it's a special data type that's basically just an integer, and then they're storing integer data. We're storing characters, we're storing strings, so instead of int we have char star, but this is basically the same. What are we doing here? Malloc, we're mallocing this. We set size to 0, we set capacity to capacity. So this all looks very similar. They're not mallocing. I don't know why they're not allocating for dynamic array struct. Maybe they do that beforehand. Oh yeah, they do. They definitely do, because they're passing it in here. So yeah, I mean, we're basically implementing vectors here, but we're just calling them arrays. What is a function prototype and how to implement it? So prototypes are, I think this is what you're asking. If you look in header files, let's see, arrays.h. If you look in the header files, you'll see copies of all of our different functions. Now these, what these are saying is, this is telling, like, our test, for example. You see our tests include arrays.h. This is telling arrays.h exactly what it can expect. So it's saying we're going to have this function called destroy array. It's going to take an array as an argument, and it's going to return void. Array read takes an array and an index, and it returns a character star, and so on. So this is just what this is what goes in the header file to tell anyone else who wants to use our code what's available to it. All right, 1 minute left. When destroying the array struct, is it necessary to go through each element pointer to free it? It's necessary to go through each element that has been allocated to free it, yes. But you don't need to free the slots with unallocated memory. All right, and that brings us to the end of official lecture, just in time, with seconds to spare. So again, looks like we have a brown bag coming up. So if anyone wants to dip out to jump in the brown bag, you're welcome to leave. Otherwise, if anyone has any further questions for me, I'll stick around for a few more minutes. Otherwise, I guess I can let you all go on time this time. Any other questions? And tomorrow, so today, keep working on hash tables, not hash tables, on your arrays. I guess I can talk a little bit about the assignment for today. So part 2, insert, delete, and resize. So insert is going to be very similar to append. You're going to be doing this, except instead of inserting it at this specific index, which is going to be the end, you're going to probably be inserting it somewhere in the middle. So in order to do that, you're going to need to clear some space out for it first. So you're going to need to move each element over one at a time, and then you'll have some room empty to put your elements. You're going to implement resize. So where's resize? For resize, you're going to need to create another array. You can use create array with the value of capacity times 2. Copy everything over one at a time. Remember, you only need to do copy everything from 0 to count. So 0 to array.count. Copy everything over. Free the old elements array, but not the strings they point to. So that means free this and this, but don't free these strings because you're still pointing to them. And update the elements and capacity to new values. So and then you just make sure all of the new things are pointing to the old things, and that should take care of that. Would that be a decent time to use realloc? Let's see, how does realloc work? Reallocates the given area of memory. It must be previously allocated by malloc. I didn't use realloc. I just used malloc again. I guess you can try. If it works, I suppose it's okay. But I'm not sure how realloc works underneath the hood. Okay, so I think what it does is it expands if there's room. Otherwise, it allocates a new block of memory of the same size. Copying the memory area with size equal to the lesser item. I guess you could do that. I don't see why not. Yeah, if you want to use realloc, you can do that. It might be actually it would be more efficient because that means if you don't need to copy it, then you won't have to run the copy functions. But if you can also do it using malloc. But yeah, Huckman, to answer your question, I think realloc is okay, or regular malloc if you so choose. If you use realloc, make sure you understand what's going on before, and don't just do it blindly. Remove. I think something. Again, when you remove something in the middle, well, first you're going to need to walk through your array and find what the index to remove is, and then you're going to need to free stuff up accordingly. So and then you'll need to scoot all the stuff over to the left this time to make sure that there's no holes in your array. All right. Any other questions about your assignment for today? Part 2. If not, then I will see you tomorrow. And again, I'll send you. I'll be dropping the hash table. Excuse me, hash table videos to watch. If you scroll to the top, if you want to get a jump, if you finished your array assignment and you want to get a jump on this stuff, you can check these out ahead of time. And hash tables are going to be here again. And we'll also keep talking more about architecture and computation theory tomorrow morning as well. So yeah, good luck. Drop questions and help, and I'll see you all tomorrow. Thanks, everyone.